Part 2. Before anything new, 90 seconds rebuilding what Part 1 left on the table. Because you may not have watched it, and even if you did, it was a lot of algebra to be carrying. The problem. You have a map, 3 points whose world positions you know, surveyed. A picture where those 3 landed in your image in pixels. And a calibrated camera, so the intrinsic matrix K is known. What's missing is the pose, the rotation R and translation T that say where the camera was standing. That's perspective and point. And one sentence carries the whole thing. The image gives you the angles, the map gives you the lengths, and the pose is whatever makes the two agree. Watch it do real work. The angles. Take a pixel, multiply by K inverse, and you get a direction, the ray that point came in on. 3 points, 3 rays out of one camera center, so you know the 3 angles between them, alpha, beta, gamma, from the picture alone. The lengths. From the map, you know the triangle's 3 sides, A, B, C. So the only unknowns left are how far each point is from the camera, S1, S2, S3. Get those and you're finished. You'd know the 3 points in camera coordinates and world coordinates, and lining up 2 copies of one triangle hands you R and T. 3 unknowns, and the law of cosines gives exactly 3 equations, 1 per side. A squared equals S2 squared plus S3 squared minus twice S2 S3 cosine alpha. 2 more like it. Known on the left, unknown on the right. Part 1 ground those down. Divide through by S1 to trade 3 distances for 2 ratios, U and V, then eliminate. That's Grunert, 1841, and it is an afternoon of algebra. Out falls a single polynomial in V alone. Its degree is 4. That's where Part 1 stopped, and it's where the trouble starts. So the whole of the minimal problem funnels down to one polynomial in one unknown. If that were degree 1, we'd have a pose and no video. But degree 4. A quartic can have 4 real roots, and every positive root is a genuinely different v, which unwinds into genuinely different distances, which build a genuinely different tetrahedron. Same base triangle, same 3 viewing angles, different camera. That's the opening scene explained. Those 4 perfect cameras weren't a bug or a numerical accident. They were the 4 real roots of one quartic. And I found that configuration by search, because 4 valid solutions is the exception, not the rule. Often 2 roots go complex and you get just 2 candidates. But 4 is the ceiling, and the algebra is why. The answer count was decided the moment the elimination produced degree 4. So how do you pick the real one? You pay for it, with information the 3 points never had. Option 1, a 4th point. Project it through all 4 candidates. In our scene, the imposters missed by 39, 165, and 249 pixels. The true camera stayed at 0. 1 extra point, ambiguity gone. That's exactly why OpenCV's Solve PNP with the P3P flag demands 4 points, not 3. 3 to solve, 1 to vote. Option 2, if you're tracking, you solved the same problem a 30th of a second ago. Keep the candidate nearest the last pose. Free, and in video, it's usually enough. Hold on though. We were promised a rotation and a translation, and so far we have 3 lengths. 1 step remains, and it's a beautiful one. Each distance slides its point down its ray. The point sits at SI times D hat I. Multiply, and we now hold the coordinates of all 3 points in the camera frame. But the map gave us the same 3 points in the world frame. The same triangle, written in 2 languages. And translate between 2 3D languages is a solved problem, absolute orientation. Subtract each cloud centroid, build the 3x3 covariance between them, take its SVD, and the rotation drops out. The translation is whatever's left between the centroids. On this channel, that's an old friend. It's exactly the Procrustes alignment from the shape analysis video, doing a cameo. Run it here and the pose comes back to machine precision. Step back and look at the whole machine, because it's the through line made literal. The image gave the angles, K inverse, dot products. The map gave the lengths, A, B, C, and then the quartic turned angles plus lengths into distances. And the pose? The pose is the agreement, the R and T that lay the world triangle exactly onto the camera triangle. Rays, cosines, a quartic, and alignment. That's P3P, complete. Every piece on the table. Nothing waved through. Before we scale up, the honest part, there's a place in space where everything we just built quietly falls apart. Not wrong, fragile. Take the circle through our 3 points and extrude it straight up, perpendicular to their plane. An infinite cylinder with the triangle inscribed inside. Old photogrammetry books call it the danger cylinder, and the name is earned. When the camera center sits on that surface, 2 of the quartic's 4 roots collide into a double root. I measured it. Off the cylinder, the 2 nearest roots sit about 1/10 apart. On it, 4 times 10 to the minus 7. 2 candidate cameras merge into 1, and a double root is a cliff edge. Right at a repeated root, the polynomial slope is 0, so the tiniest nudge to the coefficients slides the root a long way. And our coefficients come from measured pixels, which always carry noise. Here's the experiment. Same triangle, same amount of noise, 1/3 of a pixel, 400 trials each. Camera off the cylinder, median rotation error 0.15 degrees. Camera on it, 14.5 degrees. Same solver, same noise, 98 times worse purely because of where the camera stood. Practical rule, with a marker flat in view and the camera hovering near that surface, near symmetric, straight-on viewpoints are the classic case. Expect pose jitter and either move or add points. Which is the real cure anyway. 3 points we've now solved and stress tested. But a real system doesn't have 3 points. It has 300, they're noisy, and some of the matches are simply lies. That's part 2. So much for 3 points. Everything up to here has been the minimal problem, the fewest points that pin a pose at all, solved exactly, in closed form, with a failure mode we went and stood on. It is a beautiful piece of machinery, and it is not what anybody actually runs. Because a real system doesn't get 3 points, it gets 300, noisy, redundant, and some of them simply wrong. 60 points now, not 3, and the goal flips. With 3 points, we solved exactly. With 60 noisy ones, no pose explains everything, and we want the pose the whole crowd votes for. For that, we need the constraints in a shape a computer loves, linear. Start from the full projection equation. Depth S times the pixel written as a 3 vector equals K times R times the world point plus T. First move, stop treating K, R, and T as 3 separate actors. Multiply them out into a single 3x4 matrix. Call it P. 12 numbers that carry the whole camera. Intrinsics and pose fused. Name its rows: P1 transpose, P2 transpose, P3 transpose. Second move, and this is the classic trick, kill the depth. Look at the third row of the equation. It says S equals P3 transpose times the point. The nuisance unknown has its own formula. So divide the first 2 rows by the third. U equals P1 transpose X over P3 transpose X. Same for V with P2. One multiplication away from linear. Cross multiply and each becomes P1 transpose X minus U times P3 transpose X equals 0. No division left, no depth left, and the 12 entries of P appear linearly. Every point donates 2 equations of exactly this shape. 60 points, 120 equations patiently waiting to vote. Stack all those equations into a matrix. Each point writes 2 rows. The 12 unknowns of P line up as a vector, little p. The whole system is A times P equals 0. With A 2n rows tall, and 12 columns wide. This construction has a name you'll meet everywhere: the direct linear transform, DLT. So, 12 unknowns, 2 equations per point, 6 points. But why 6 when part 1 solved with 3? Because this method knows less. P has 12 entries, but scale it by any constant and the divisions cancel. Same camera. 11 honest degrees of freedom, so we need 11 equations, 6 points. Part 1 used the fact that R is a rotation. That knowledge was worth the 3 missing points. The linear method trades that knowledge away for linearity. Don't take the counting on faith. The matrix will tell us itself through its singular values. A true solution of AP equals 0 means A has a null direction, a smallest singular value of 0. 4 points, smallest singular value 0.66. No solution yet. 5, 0.07. Still no. 6, 10 to the minus 15. The null space snaps into existence exactly on schedule. And with noise, no exact null vector exists, so take the singular vector with the smallest singular value. The direction A squashes hardest. That's the SVD recipe, and it's the same least squares hammer this channel used for homographies. Reshape those 12 numbers into 3 rows, and P is ours. And that is exactly the cliff to stop on. P is not the pose. 12 numbers that behave like a camera, pulled out of a null space, but R and T are still buried inside them, tangled together with K, and with a scale the homogeneous solve never pinned down. Worse, nothing in that linear system ever knew that R had to be a rotation. It fitted 12 free numbers and handed them back. Part 3 unpacks all of that, and then throws the algebraic answer away in favor of the only thing you actually care about, which is what the picture looks like. Part 3. Many points, one pose. See you there.